Welcome back. In this video I'm going to do the solutions to the two problems at the end of the substitution section. So we'll start with the integral of 4e to the 7x. So notice that the 7 is what's causing trouble in this particular integral. If we just had 4e to the x, we'd be good. E to the x, the 4 would carry down, e to the x is its own derivative, so we would just have 4e to the x and we'd be good. So I can tell right here there is a linear function where I wish that there was just a plain variable. That's a good indicator that this substitution strategy is going to work. So I'm going to choose that 7x to be my u. So I'll choose u equals 7x. Alright, so once I make that choice, then I have to compute the du step every time. That should always be what comes next. So on the left, I always have du. The derivative of 7x is 7, and then we always throw in that dx. So the du here and the dx here are always in that step, and then here you'll just have whatever the actual derivative was. Okay, so if this 4 happened to be a 7, we would have 7 dx, and we would have a perfect substitution for it. But usually that's not the case, and it isn't here. So we have one more step to take, which is divide that 7 onto the left-hand side. So all I've done is divide both sides by 7, so I've got a 1/7 here. Now what I have is a substitution for just dx. So this can become e to the u, and then the dx I can put in 1/7 du. And having extra constants, is no big deal, so that 1/7, we can totally work with in terms of integrating. Okay, so I'm going to make my swap and kind of hope that this will work out. So we have 4 e to the, instead of 7x, we'll say u. And then instead of dx, I have 1/7 du. Okay, so one challenge we've definitely accomplished in that we switched it entirely from x's to u's. That's always one hurdle. And then the second hurdle is to make sure that what you're left with here is actually something you can integrate, right? Like you can do all this work and then get here and still have something that's too complicated to have an integration rule. But in this particular example, it's working out nicely. This isn't in its best format, but it's, it's workable, right? So in my next step, the 4 and the 1/7 I'll combine. So I just have the integral of 4/7 e to the u du. So I just have a number times e to the variable, and that's something I do have an integration rule for. 4/7 carries down because it's a multiple. E to the u is its own derivative, and of course that plus c. Now that I've actually integrated, and it looks like I didn't do anything just because this happens to be its own integral, but technically I've integrated. The integral and the du are gone. As soon as I take this step, now it's time to switch back from u to x. You always want to make sure you end by switching back into x's. And it will only require just the original substitution. U is 7x. So that's what I'm going to write in that spot in my last line. So I have 4/7 e to the 7x plus c. And again, if you're feeling really ambitious or thorough, what you could do is take the derivative of this function and show yourself it really is the original integrand. All right, so we'll move on to the second example here. We've got 3 times the square root of 2 minus 6x. This 3 is a multiple on the outside because it's like big and kind of like off to the side. If it were a cube root, it would look more like that. I know sometimes it's really tough to tell the difference, but this will be 3 times the square root here, so this is not that. Okay, so it's 2 minus 6x here that is causing trouble, right? If this was just 3 times the square root of your variable, you'd be good. So that tells us that substituting u equals 2 minus 6x would probably be the right call. So that's what I'm going to try and see if it works out. And if you remember up here, we were talking about how to tell if it's, quote, working out. The two things, like you can kind of do this computation, and the two things that you want to make sure eventually happen are, one, that you can actually switch from x's into u's completely. You never want to have them both at the same time. And then the second thing is that it's something you can actually integrate. As long as both those things happen, you're good to go. All right, so this is my choice. I'm going to compute the du. That should always be the next step. So du equals The derivative of 2 is 0, and then I have minus 6 from the minus 6x. So du is negative 6 dx. And just like in the problem above, when I need to divide by 7, I need to divide by that negative 6 so that I can just do a clean substitution for dx. So I'll have negative 1/6 du equals dx. All right, so now here I can have 3, the root of what I called u, and then dx has this whole substitution here, negative 1/6 du. All right, so I will make that swap. So I still have 3 square root of u, and then dx is negative 1/6 du. Okay, so we've made a lot of progress. We've completely gotten all of the x's out of there. I do want to clean up the constants, right? I've got this 3 and this negative 1/6. If I combine them, I get negative 3/6, which is negative 1/2. The square root of u, I'm also going to rewrite as u to the 1/2 power. Only because I need to use the power rule to integrate this thing, and I like to actually see it with the number on it, but it's not technically entirely necessary. All right, so now I can actually integrate. The negative 1/2 carries down. U to the 1/2, I'll use the power rule. So I have 1 over 1/2 plus 1 times u to that same number. Okay, so we've got a little bit of cleanup with the constants here. And then I also am going to swap out the u for 2 minus 6x. So let's take care of these constants first. So that would be negative 1/2 times 2/3. The 2's cancel, and I get negative 1/3. So I'll have negative 1/3 times u, which will go back to 2 minus 6x, all raised to the 3/2, and then plus c. And sure enough, if you think about taking the derivative of this thing using the chain rule, once you get that times negative 6 at the end of the chain rule, it really does simplify to the original integrand. That was fun.